Hello and welcome to the class. Hi everyone. Hi. Um, let's see who all are there. Hi. Anuj, Arjun, Chaitanya. Chaitanya, good that you made the new Gmail account. Uh, okay. Good. Devanshi, Gaurav, Hardika, Mayank, Mohammed, Fahim, Nadir, Nero. I forget again Nero. Who is Nero? And Niranjan, Prasanna, Ronak, Sachin, Shisha, Sumira, Vedant, Vignesh, Viral. So many people. Okay. Good. Hi. Good afternoon, everyone. Madhav, also good afternoon. So, yeah, I hope the sound and all is good. You can hear me. Can you hear me? Just give me a message, and I hope the video quality and audio quality, everything is good. I'll remove the monitor. Yeah. Okay. So let's start off with the class. Right. So we are doing the day 2, right? And yeah, Nero is Shivam. Yes, I forgot. Right. Okay. Let's start off. So we are on day 2, and I think yesterday's stream got a little bit longer than I anticipated. I thought I would probably complete it in an hour, but it seems like it went for a little longer than I anticipated. I'll try to keep it, shorter this time around. Did you guys get all the information that I sent you through the OneNote application? I put up some interesting videos for you to watch. I put up some reference materials, specifically from the book, this book. Yeah. So I put this up, and I put the other Rob Thompson book also, and I think I also put another interesting book by Jim Lesko. Just see those materials, and you'll be able to follow through the class. Okay. Chaitanya, thank you for that. We love the class, and you can go on for hours. But I would want to keep it to as short as possible, because I want to have these videos up also. So if somebody is watching a recorded video, he shouldn't get bored, or she shouldn't get bored as much. So considering that, and besides that, I think shorter videos are also a little more engaging in that manner. But anyway, let's start off. So let's start off with the class, right? So we discussed this yesterday, and right. So we discussed the kind of materials that are there, and from here on, in this class, what we are going to discuss primarily is about properties of material. Okay, and just hold on. Right. So what do I mean by properties of materials? Right. So there are some interesting properties of materials which help us determine the uses of it. Okay, so like for example, some mechanical properties are important when you are designing, for strength of a part, right? Things like ductility, elasticity, hardness. We will discuss what each of these properties are. Some of them I think you already know. Some may be new terms, like maybe fatigue is a new term for you. We will discuss very briefly what these are, and we will try to analyze how they may help us in the whole design process. And then there are some physical and chemical properties of materials, right? So these are like density, melting point, specific heat, and so on and so forth. So this slide has got a few of these properties which are important for for us to consider when selecting a material or designing a part with that material which will go into a product. Okay, so as you can see, there are four ways in which it is categorized. The first one is the structure of material. The molecular or the elemental structure of materials, right? By that I mean how at the atomic, subatomic level or atomic level, the atoms of a certain element are arranged, and that kind of affects the properties as we go on. So this atomic properties kind of affect the mechanical properties and the other properties, so on and so forth, right? But we will not go too much into details of that. We will just do a basic overview. Some of these topics you've already learned in your earlier classes, or rather I should say in your school, in your subjects. So let's take a look at some of these, right? So I think most of you know about this. You are aware of these diagrams. Okay, here I want to, put a little disclaimer, because once this live stream is done, the video will be recorded and it will be up on YouTube, and there is a lot of things related to copyrights and all of that, which is important for us to consider. But since these sets of slides were earlier prepared for a very for delivery at a class level, so I have not really put in the sources per se. I hope that somebody does not oppose to this. If some random person is watching in the internet, the sources primarily are from this book, in Manufacturing Engineering Technology by Kalpakjian and Schmidt, I hope that I'm doing this in good faith, so I hope I don't get like DMCA notices to take down the lectures. It's only for the benefit of students. So with that disclaimer out of the way, a lot of these images have been picked up from internet, and some of them I have forgotten the sources, but I've put it up here in good faith that people will understand the reason why this video exists and why this lecture exists, and maybe consider and not make a copyright strike because of these images. Okay, anyway, okay, with that disclaimer out of the way, let's start off. So you are aware of this, right? So you are aware of something. What is this? This is a body-centered cubic structure. So generally what happens is that in pure metals, the atoms are arranged in this kind of a fashion, right? So they are packed in this kind of fashion because of various atomic forces and all that. And this is like a low energy state in which the material can exist, right? Or it's one of the state where the atoms are comfortable existing in this kind of an arrangement. So these structures help the material behave particularly in a particular fashion. So what you see here is the body-centered cubic, and some examples of materials which exist in this form are iron, specifically a type of iron called alpha iron. Okay, just like wood. Okay, we are all aware of wood, that it exists in different forms. Okay, so we are aware that wood, let's say teak wood, is different from mahogany or maple or birch or something like that, and the reason they are different is because of how the grains are oriented. So similarly, metals also exhibit some kind of similar kind of property, where the atomic structure, right, the structure in which these crystals exist, that kind of makes a different type of metal. Okay, so like for example, BCC, alpha iron is a type of iron which exists in a BCC structure. Similarly, things like chromium and molybdenum and these kind of tungsten and things like that, these exist in BCC structure. Okay. The other is the FCC, which is the atoms. If you take a cube, right, which you see over here, I should get my tablet out. Okay, so that way I think it's just a second. So if you see this kind of a structure that exists, right? So this unit cube is represented here, okay? And some kind of material such as, another form of iron which is called gamma iron. Now here I'm talking about pure elements, okay? Iron, when I say iron, it doesn't mean steel, okay? There is a very clear distinction and you should be aware of this, that you shouldn't be saying iron when you need to say steel or vice versa. So elemental iron, we are talking about elemental iron, right? Elemental iron can exist in something like gamma iron is something which exists in face-centered face-centered structure. Aluminium is a material which exists in this way. Gold, silver, things like that. And then there is one more which is like the hexagonal close packed HCP structure, and something like cadmium, beryllium, and these kind of elements exist. Now, why is it important for you to know this? Because you have to, so most of the materials that you will be dealing with as when you are trying to develop a part for a design are not going to be elemental materials. These are going to be alloys, right? And alloys are a mixture of two different, elemental elements. Okay, like for example, steel is a mixture of mostly it's a mixture of iron and carbon with a few other things added. Now, when I say mixture, it means something like salt dissolved in water. So the carbon atoms are dissolved in this lattice structure of the iron, okay? And that kind of enhances some properties of the elemental iron, and it makes it easier for us to use them in manufacturing processes, right? Okay, so here is an image which shows you a way in which the crystal structure gives way when you apply force. Okay, so let's say, so what you see here, right? So if this is like an atomic crystal structure of a certain element, if you apply force to it, so imagine this block, imagine this kind of a block, let me try to draw it, this kind of a block, right? It's made out of a single material, let's say Fe, right? So let's say alpha Fe. So this is a type of iron, okay? So if you, and this is like a fairly big block, right? So let's say this is 10 cm by 10 cm, something like that, okay? And it is made out of a single crystal structure, okay? So crystals are arranged properly, so throughout this whole cube, right? Now if you apply a force in a certain manner, let's say you apply one side this way, one side this way, then what happens is that this kind of a thing happens, okay? And you get these like places where the crystal kind of gives way, and this is how it breaks, right? Sorry, not this, right? So this is how it breaks. So that's something to keep in mind, that when you are applying force to a certain part of certain material, what exactly happens at the molecular level, at the atomic level, or at the crystal structure level, so that fails and how does it fail. So this gives you a lot of information about the type of applications in which this material can be used. Okay, so this is this image that you see is like showing you the slip planes in at a very microscopic level, right? So at 10 nano micrometer level, I think it's nanometer. Yeah. Okay. So and this is the kind of a same thing, right? And then the other way in which it fails is if you pull it on the other way, and if let's say these two images, right? If you pull it, right, there is a way in which it fails, and these are called. This one is called twinning. So what happens is that here the grains are probably arranged in this way, and at this point they probably get arranged this way. Okay, let me clear everything, right? So here let's say it is arranged like this, but as you start applying force, some part of this area, the whole crystal structure kind of gets distorted, and you have this kind of a failure where the crystal structure reorients itself to form this kind of a twinning space. So this is called NING, twinning. Okay, anyway, okay, so right, okay, so let's move on forward. Now those things that I showed you was related to a single kind of a crystal structure where it's a single element. It's a crystal made out of a single element. Okay, most often than not, what happens is that you never get like a proper an element with a single crystal structure made out of a single element atom. Okay, so by that I mean you don't get, in the real world it is almost impossible to get a single crystal, a block which is made out of single crystal of an element without any impurities. There will always be impurities, and the impurities are arranged in the way that you see in this image, right? So you may have a place where the crystal is fine, but one of the elements is missing, or you may have a place where there is another atom of a different kind of an element which is lodged inside the crystal. Okay, you may have one atom which is like almost the same dimension as the other atom with which the rest of the crystal is made, but it has replaced that original atom. Okay, and these are the various defects that are possible. Okay, the reason why you have to know this is because this is the foundation of how alloys are made. So alloys is as I said, is a mixture of these two elements where you have the larger portion of the material is made out of a single element. Let's say in steel it is iron, but these small spaces are filled up with other kind of impurities, and in, let's say, in mild steel, I think it's mild steel, you have 0.3% of the overall spaces filled up with the carbon atom. Okay, something like that, and that is like an alloy. And now you can imagine the dispersion of these carbon atoms is something, it's not like a within the crystal, the dispersion is not something which you can just remove directly, right? So it needs a lot of effort to remove these carbon atoms from the whole crystal structure. So that is how good the mixture of the whole thing is, right? So, and that is alloys. And here I am giving you showing you two more ways in which the crystal the defects in crystal structures can be. I think this is something that is generally taught in the science subject in schools, and you may have seen this. We will not go much into detail, but it's an interesting topic to read. I suggest you read the Kalpakjan book chapter. It's the very initial chapter, and you can get an idea of how alloys and how crystal structures affect the properties of material. Okay. Now, so what we have seen is at this is like this slide shows you, let's say, at a very small scale where atoms are arranged, and I can see, okay, this is the structure in which this is arranged. Okay, this image shows you a slightly zoomed out picture where there is a lot of crystals arranged in a certain manner. Okay, and this one is, even if you zoom out even more, this is what you will see. Okay, what you will see in a piece of iron, if you look through a microscope, is these boundaries. Okay, like these boundaries. Okay, these are called grain boundaries. Okay, and the reason these form is because, let's say, this part here, this white space, is liquid material. Okay, what happens is that in liquid material there is no crystal structure. All atoms are moving around freely, but slowly, as the material starts cooling down, what you will see is some places the first crystal is formed, and then some more is formed, and then some more is formed, and there's like a small area where the crystals have formed in a certain manner. So let's say this one is, let's say, an alpha iron, okay, which is like a BCC. Okay, BCC, and similarly there's some more areas where another crystal forms and some more is formed. Now, as you can see, the orientation of all of these is slightly different. So this one is probably, let's say, it is oriented like this and like this. Okay, this one is oriented like this and like this, and this one is oriented like this, and so on, right? This one is oriented like this. Okay, as these grow, what happens is that the new crystals are formed at these locations, and these locations are called nucleation sites. So these are nucleation sites, and as the crystals are formed, you will soon have a place, a situation where the crystal can't really grow and bumps into the other growing group of crystals. Okay, and this as the material cools down, you get these kind of boundaries which are formed. So these are called grain boundaries, and these have a tremendous effect on the properties of material, especially steel. If you are able, metallurgists control the size and the shape of the grain through various processes. Like, let's say, forging is a process, right? So when you forge, you can control the shape and the flow of the grains. So here you don't necessarily see the flow of the grains, right? So, but let's say you have a piece like this, and you have a bucket of molten material, and you cool it from this side, right? So what happens is that you will get a crystal structure which is something like this. Larger crystals are formed here because when the nucleation started happening, all of this was molten, and the crystal was able to grow along these lines. Okay, and as it goes forwards, you have smaller and smaller and smaller grain sizes. And so now, as you can see, so finally, when this thing is cooled down, you will probably have a space something like this, the grains arranged in some manner like this. So there is a definite direction to the grains, orientation of the grains, and this has a lot of effect, and the way the grains sizes are there has a lot of effect on the properties of the material. Okay, so I have a small let's see if it runs. There's no sound here. So here you can see actually material getting cooled down, and the grain boundaries kind of disintegrating and merging into each other. Okay, so I'll leave this up in the presentation, and you can see it later, and you can observe very closely how things are, and this is actually the real thing. Okay, the other, just as I said, let's say if you have, let's say, a solid or rather a block of liquid metal, and you expose it to air, what happens is that it will start cooling from the outside, right? So there's chances the most amount of heat that is removed is from the outside, so you will get this kind of grain boundary arrangement. Okay, now grain, so as in the previous slide I said, each one of these dots have the grains oriented in a certain manner. Which manner we are not particularly concerned with, but each one of these grains forms like a space within which the crystal can be found, crystal arrangement can be found. Now you can see this in a lot of other places. Now if I just do a Google search of, let me see, okay, I will try to show you. Okay. Just a second, I'm doing like a image search. I don't know if you'll be able to see. Okay. Right. Okay. So right. So I've done in California. There is a lake, a reservoir rather, where to shade the water from direct exposure to the sun, they release these black colored balls, okay, onto the lake surface. Okay, the reason why it is there, there's like a very nice video by this guy, Veritasium. I think the channel's name is Veritasium, and if you go and see, then you know the reasons. Now the reason I wanted to show you this is, once the balls have filled up the lakes, you would imagine that it will look like a uniform field, okay, with black balls. But no, what you see here is like you can clearly make out like a boundary. Yeah, so if you can see, there is a clear boundary of the balls. So inside this, there's a clear arrangement of the balls in a certain direction, and inside this boundary, there is a clear arrangement in a certain other direction, right? And this is exactly how grains are formed inside the material. You can imagine each of these as an atom, okay, and imagine if it cools down, it's not necessary that you'll have a uniform pattern with filled up with balls, but you will get these kind of boundaries which are forming, and these are the crystal boundaries, these are the grain boundaries. Okay, right, so let me clear this. Okay, so moving forward, let's see if there are there. Did you see, Devanshi? Did you see what I was talking about? Please tell me you saw the black balls. Okay, otherwise I'll show you again. Anyway, so moving forward, this chart is shows you the properties of various materials at room temperature. Okay, like for example, in terms of strength, right? You see that glass fibers are the strongest and lead is the weakest of materials. Okay, hardness, diamond, we all, I mean, I think this is like a GK question in class 5 or 6, which is the hardest material. Diamond is the hardest material, right? And lead is the smallest, softest material. Toughness, okay, reinforced plastics and thermoplastics are tough, whereas glass is not tough. Okay, so now it is becoming a slightly confusing thing. What exactly is toughness? Okay, and what exactly is hardness? Okay, there are specific ways in which we define these terminologies, like stiffness, strength, strength upon density. These are all mechanical properties which are important for us to know about in a material, okay, while selecting a material. Okay, so I want you to do search and find out and understand very clearly what is toughness and what is stiffness. Okay, we will discuss still, but let's move forward. Okay, there's some homework for you on this. Right, so again, this is one of those slides where I ask the students, can you tell me which material is elastic and which material is not elastic? Okay, something like that. But I will keep this slide here for you. There are two, the important point to take out from this slide is there are two very important properties of material that we should know about when selecting materials. Then these are stress and strain, or rather how much can a material, WBN is the hardest, I believe. I think it's not a naturally occurring material, but I may be wrong. I don't know what WBN is. Ace says WBN is the hardest, I believe. Okay, we will see. So you have read about the Hooke's law. So Hooke's law defines a constant called modulus of elasticity, and it is the ratio between the stress and the strain in a material. Okay, when so what is stress? Stress is the amount of force per unit area that is applied to that material. Okay, let's say a standard piece is taken, a standard, let's say a cylinder is taken, and in that you apply force on both ends. Okay, so certain amount of force you apply, and you can if you take the cross section area, if you divide that force by that cross section area, then you will find the stress that part is withstanding. I mean, as long as it is not breaking, that part withstands that stress, right? Strain is the amount of elongation, or rather is the ratio of the elongation to the strength, to the length. Okay, so let's say it's again a cylindrical part. We apply a force enough to move the piece, okay, stretch the piece a little bit. So how much it has stretched by the length that it was originally, that is the strain that particular piece is going through. Okay, and the ratio of the stress and strain is the Hooke's law. Okay, I think you know all of this. I mean, I spent a little time explaining, and this chart also I think many of you are aware of. Rather than explaining this chart, we will take a look at a video that I have, and we'll understand that this chart through that process. So this chart is a result of a tensile test. Okay, and it plots out the stress on one side and the strain on the other side, and what the line means is that as you apply more and more stress to the material, there is a certain amount of strain that you will see, right? So that means there is a certain amount of elongation, okay, that will happen in the part. Okay, and this part that you see at the side, this one, is a typical part which is used to do this kind of a test. Okay, so this is the shape of the part. The reason there are these grooves are so that a clamp can be put on either end and the force can be applied in a uniform manner. Okay, and what happens is that for most metals, I should say, okay, I can say most metals. For most metals, what happens? You will see a area, a part of the graph which is a perfect straight line. Okay, which is almost a perfect straight line. So this straight line means that there is a linear relationship between the stress and the strain. There you can there is a proportional relationship, right? So you give X amount of stress, there is Y amount of strain. Okay, and you can find a mathematical formula, and the mathematical formula naturally is the Hooke's law, right? Now there will be a point where this piece will not be able to withstand so much pressure load that you are applying onto it. So what happens is that you will reach this area. From when on, there will be more strain. So that means when I say more strain, that means the ratio of the change in length by the length, right? So that ratio increases. That means the changing length really drastically increases, but you are really not applying too much force. So what happens is, so you can, okay, I'm going to say something a little disgusting here, but you can see this. Okay, you take take a chewing gum. You eat the chewing gum, and if you're not disgusted by it, you take it out, you hold it nicely, and you apply a little bit of force. And at one point, if once you start applying just a little bit of force, it will start going elongating, right? So with very little application of stress, the part is seeing a huge amount of, Aditya, don't do with boogers, please. Okay. First material is elastic, is what Shreya and Devanshi are saying, right? Okay, we'll come to this. Okay. Right, okay, and then there will be a point where without even applying any force, the material, if you just, if with the existing amount of force that is there, that you've already applied by this time, with that same amount of force, the material will keep on elongating without applying any additional stress. Okay, so what happens is that this point is called the ultimate tensile strength. So this is the point where the material has started failing, and then as you will not be able to apply more stress because the material has started deforming so much that the internal stress, there is a loss in internal stresses. So if you calculate the amount of stress that the part is withstanding, decreases. Okay, and at one point, so this area where the graph comes down is the necking area, and at one point the material will break. Okay, and this is what you will see has happened. Okay, and so let's see, let's go forward and we will see a video where this chart is explained properly. So you can remember these pointers that I have said, and you will probably realize what the video is talking about. Okay, again, the video was downloaded from YouTube some time back to ensure that internet is not a problem when I'm giving the lecture, but now I may get a copyright strike, in which case the lecture is lost, right? So that is a problem. Anyway, okay. Right. So what you saw here, the Hooke's law, is actually, I shouldn't say wrong, but it is slightly misguided, because what happens is that one thing that is not considered in the Hooke's law is, as you are changing the, as you are applying more and more force, as the part is experiencing some amount of strain, there is a distinct change in dimensions of the part. Okay, so that means the area gets reduced. So that is not considered in the Hooke's law. Okay, but you when you want to calculate it more accurately. No, Cyril, I think the video, I saw the message, the video is public right now. Okay, anyway, let's move on. So, as I said, in the Hooke's law, that change in area is not considered. So, we can calculate the true stress and true strain with by considering this change in area. Okay, and there is like a, integral way of calculating using integration. You can calculate this kind of thing, but it's not important. I've kept this equation here for you to reference it lecture. Okay. Ace says you won't lose the lecture, it will just get demonetized. Yeah, anyway, I'm not looking to make money out of this, but yeah, okay. Right, so that was the Hooke's law, and so the ratio of the stress and strain is called the modulus of elasticity. I think that was clear, right? Or the Young's modulus, or the modulus of elasticity. There are other two more constants which we will not talk here, but if you read the section on the Kalpakjan book, you will get to know all of this, and I suggest you do that. Okay, right. Okay, so here in this slide we are showing, it shows you the modulus of elasticity of the Young's modulus, the ultimate tensile stress, and the modulus of elasticity of these various materials. Okay, so aluminum and its alloys generally have a modulus of elasticity of around 69 to 79 gigapascals, whereas the Young's modulus is, so the Young's modulus the yield strength, I think the Y is the yield strength. Okay, Y is the yield strength, and UTS is the ultimate tensile strength, right? So yield strength goes from around 35 to 550. So you can see, based on this chart, you can kind of analyze which are the strongest of all materials and alloys and its alloys. So especially the range, for example, molybdenum and its alloys have a tremendous range of yield strength, right? So they the amount of strength that you would require to kind of reach a point wherein the part is no longer usable, right? You need a significant amount of stress if you take a certain type of molybdenum alloy. So this chart really helps you to understand that. Okay, right. Okay, I'll keep this up. There's no point discussing numbers. I mean, it's there for you to reference. If I'll also not ask it in the test. What is the yield strength of titanium and its alloys? I don't expect you to remember, but it's there. So let's take a look at this video, and we will discuss. We will pause the video. One thing I want to tell you, just tell me if you can hear the, if you can hear, I think. Just tell me if you can hear the, sound of it.
The tensile test. First test, material with yield point.
Just a second, I think there might be like an echo.
In the tensile test, a plain carbon steel with yield point phenomenon is to be tested.
Right, okay.
This is the test piece. It has
if you can hear it without an echo, it's
an
good.
Original diameter of 10 millimeters and an original gauge length of 100 millimeters.
Sorry, what happened?
Within
I think there's...
In this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand Control, the tester moves the upper cross head into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips.
So this is the test piece that I was talking to you about, right? And as you can see, it has these grooves at the end so that you can clamp it nicely. And this guy has drawn some markings on the on the test piece for him to be able to easily visualize the whole thing. Okay.
In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer.
Right, I'm sorry. I am terribly sorry. Let's
swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters.
So the extensometer is basically like a device to help you see how much elongation has happened and what is it's a device for calibration of the whole test, okay?
On the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters.
So this is I think is a video explaining not just the tensile strength, but this kind of a machine and the company who makes these machines kind of puts up these videos. So it's a really good resource for students. So that's why I put it over here. And
during the tensile test, the test piece is slowly and constantly elongated with a standardized speed.
So here you can see on the side you have something in kilonewtons, which is the force which is being applied, and he's saying WEG. I think it's in German, but so this is the actual elongation. This is not the strain. But it is going to be representative of the same thing, right? So
the force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically.
Yeah, so note what she said, the narrator. She says that during this time when you are seeing this kind of a straight line, the material behaves elastically. What does that mean? So it's important to know what that means. That means during this time, the material is able to withstand its force even by moving a little bit. Okay. And when that force is removed, the material would come back to its original dimension. So this is one of the key important ideas when you are designing a part which should withstand load. Okay. Especially let's say tensile load. Let's say bridges, right? You have to design a part which goes into a bridge which will come under a tensile stress. Okay. So you have to ensure that that part as far as possible remains within this straight line area. The stresses never exceed a point which does not fall within the straight line. So that's why this is very important.
If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation.
So she mentioned something. In a material with yield point phenomenon, okay, so this is a key statement. So there are some materials which display a very distinct point from where there is there is no longer a linear relationship between the stress and the strain, right? That means there is a distinct point from where once you start applying the force, it will not proportionally change the strain. So it will there will be more strain for a little bit of force that you apply. So that point can sometimes be seen directly in some materials, and those materials are said to be the ones which exhibit this yield point phenomenon. Okay, so the yield point is the point till where this straight line exists. Again, oh my god, I'm sorry. Let's
area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs.
So think about what is actually happening. You can't really visually see it in the specimen after it till it reaches a certain point, right? But till now, the length of the test piece has increased slightly, and now at this point, what is happening is that there is certain amount of increase which is happening, but the internal stresses are not changing. You are applying the force, but the internally the material is kind of giving way. Okay, that means it's not withstanding that stress. Okay, so that is what is happening at this point.
This phenomenon is called the Ludus effect. After a certain strain, known as the Ludus strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens.
Okay, here is an interesting terminology which is strain hardening. So what is happening is that as you are applying this force in the material is, as I said, is made out of these crystal structures and all of these, right? Grain boundaries and crystal structures. So internally, what is happening? Imagine, why does the material elongate, right? There must be some amount of crystals which are kind of breaking, right? Which are changing its shape from its original shape, and these atoms are probably shifting to a new positions, and newer crystals are probably not newer crystals, but the orientation of the crystals are changing, or the grain boundaries are probably separating, right? They are disintegrating. So because of this internal phenomena, something called strain hardening happens, which is the material kind of is able to withstand a little more stress because of this internal locking of the grains, or the arrangement of the crystals, I should say it that way. Okay.
Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner, but keeps a cylindrical shape.
So now you can start seeing the deformation on the left hand side very clearly.
As soon as the
force is being
reached,
applied,
the neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece.
Right. So this is at one point so till now what was happening is that the whole test piece was getting modified as you applied these force. Okay. But as soon as this one point is reached, the effect of these stresses, the strain that is actually happening, gets localized. Okay. And this localization of the effect of the stresses can be seen in the formation of a neck. Okay. And you'll see there.
Fractures there.
And it's going to go 1, 2. Break. Right? So this is what happened. Okay? And you can see this graph, which is like a beautiful representation of the graph. It is slightly different than the graph that I showed you, because the graph that I showed you was not for a material which displayed a yield point phenomenon. Okay, this material displays a yield point, and most likely it is steel. Okay, it may be a specific type of steel. I am not sure what, but most likely it is steel. Okay. Now let's go forward into this video and
In the
see.
recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically.
Yeah.
FEL is defined as the force at the lower yield point, Fmax as the maximum force.
Right. Devanshi asks what determines the position of the neck. I cannot clearly give you an answer, but I'm only guessing right now. So I think it is the overall dimensions of the part. Okay. So it's the stresses kind of build up into a point where where it is most likely to fail. I mean by that, so let's say you have a cylindrical piece and you have a small cut at one point, there's a groove of one point, so there's a change in dimension somewhere, right? So the stresses kind of get localized there, and I think the neck would form there, but I'm guessing right now. I'm trying to do like an educated guess, but yeah, I think that is what happens. Okay, here one thing I would like to point out in this chart is that the thing that should concern designers is the FEH, FEL level, right? You should always design Aditya asks, the force in the graph is the force applied by the machine or the resisting force in the rod. It is the resisting force. It is the force that is resisted by the rod, the internal stress in the rod. Okay, it is directly naturally related to the force that you are applying, but what is being measured is the stress in the part. Okay. So for designers, it's important to see these 2 points. Okay, so you should never design a part which will which is designed to withstand only this load. Okay, so that means let's say I have a tripod like this, let's say, and this part I have designed so something weight is always kept over here, and this, when I keep that weight over here, it will experience a stress of FEH. Okay, that's never a good idea, right? What if there is some amount of extra forces somehow that comes in? So you always employ something called a factor of safety. You design for a load which is probably just 1.5 times or 2 times lesser than this, like half of this. Okay, so the maximum forces that this part can withstand, it will probably be half of this. So that's like a thumb rule that is generally followed in engineering, and the reason that is done is because you can never anticipate all the forces, all the loads that a part will undergo. Okay, there will definitely be, let's say, a tensile stress that may be applied to a part, but what if there is like a compressive stress that is applied? What if there is some kind of shear stress? That means by shear I mean I'm pushing one side this way and one side this way. Okay, so somehow, let's say because of wind or something like that, that kind of forces come into play. So ensuring that you are designing at like 1.5 factor of safety level ensures somewhat by a thumb rule that these other forces or other stresses are also considered in the part. Okay, so
using these forces, the strength properties of materials can be calculated.
So let's just see the calculations.
H is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength Rm. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined.
Yeah. So
this is the permanent strain after fracture.
So this is what was initially put in
this example.
And look at the amount of
Please
change
note
that is
that
there.
The percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area.
Right, okay.
In the second tensile test, a material without yield point phenomenon is to be tested.
So this is what, this most likely is an...
It is a precipitation-strengthened aluminium alloy.
Yeah, so it is an
the
aluminium
test piece
alloy.
Has exactly the same shape and dimensions as the specimen in the first test.
So right, so as you can see, we are using a specific type of a specimen, okay? So this is a standardized dimension. So the graphs that you see that the stress strain graphs that you see are of this specific dimension. So if you change the dimension, naturally I think some things would change, but it is standardized for us to make a good engineering judgment of how this material will behave. Okay.
It is cylindrical with an original diameter of 10 millimeters and an original gauge length of 100 millimeters.
And
after fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start.
Yeah, so the same thing happens, and let's see how this graph is different from the other, right? So let's see the whole test. And yeah,
the initial linear curve in the force elongation diagram again shows the elastic behavior of the material.
So at this point, if you leave the material, it will come back to its original dimension. Okay.
But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. So there is a smooth and gradual transition from linear elastic behavior to plastic deformation.
So you can see the part moving on the left hand side.
The force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops and all subsequent plastic deformation is confined to this neck until fracture finally occurs there.
Right? Okay.
As a common substitute for the yield strength, the 0.2% proof strength
can you normalize the volumes? Okay, I'll try to normalize the volumes a little bit. I'm sorry.
Is used. It is
I've changed the volumes.
the stress that causes 0.2% of plastic deformation in the material. And this is the way to calculate it. First of all, the elongation that corresponds to 0.2% of strain has to be computed. For an initial gauge length of 100 millimeters, the result is 0.2 millimeters.
So what she's trying to do here, okay, in a material with distinct yield point phenomenon, you can clearly say that this is the elastic range of the material. Okay, yeah, okay. But with material which do not show a yield point phenomena, how do you say that this is the elastic range of the material? Because there is a smooth gradation. So what they do is they've taken like a standardized measurement. Okay, so they say that okay, till 0.2% of the dimension of the test piece, which comes to 0.2 mm, we will consider that as not really having any change in the test piece. We won't consider that change. So with that idea in mind, what she'll do is she'll draw a straight line.
In the force elongation diagram, a straight line parallel to the elastic line is drawn through the offset point of 0.2 millimeters of elongation. The force at the intersection point of the offset line with the force elongation diagram is designated as Fp 0.2. This is the force that causes a plastic strain of 0.2%.
So this is the this will be considered as this Rp 0.2 is considered the yield point of the material. Okay.
0.2% proof strength Rp 0.2 is equal to Fp 0.2 divided by the original cross-sectional area
So we
F0.
need not see this part.
Tensile strength percent.
It will be there for you. The video will be there for you in the presentation, so go through it. It's a very informative video, and there are a lot of things that I did not explain in this video, so you need to look at the video, Google all of these terms and figure out and read about it in the books, right? So now I will go back to one of my previous slides, and I will ask the question again. Forget the three middle stages. Okay, don't consider these three middle stages. Okay, let's do a pen. So don't consider these three middle stages. Okay, if you don't consider these three middle stages, what do you think is the difference between this material and this material? Okay, so you can put your answers in the comment section, I think, or the chat box, and we'll move forward. Okay, right? So we saw the tensile stress for tensile test for a metal. What is the tensile? How does the Aditya says the one on the left didn't go beyond F max, or first is plastic, ductile and non-ductile is what Devanshi is saying. One of the material is something that has shown you a yield point phenomenon. The other material is something that has not shown you the yield point phenomenon. Whether it is ductile and not ductile, you can only say once you see the whole thing. But yeah, I think the one on the left hand side was ductile, more ductile. Okay. Anyway, okay. So this is the stress strain curves. What you see on the screen is the stress strain curves of how you can gauge the properties. So let's say one with a very brittle material will have a very straight stress strain curve, and suddenly there will be no more. That means it is broken here. That means it breaks here, right? A strong material which doesn't is not ductile at all, let's say like a steel wire or something like that, it will have a linear section. It will have like an elastic region, and then it will break. And some like a ductile material, both we are considering both, which shows and does not show yield point phenomenon. Something like this you will see. And a very plastic material, there will hardly be any place which is elastic, okay, where if you remove the stresses in the material, it will come back to its original point. And you will always see this place where as much stress the part is experiencing, the strain or the dimension are getting changed. Okay, right. And this for illustration only, I have put the stress strain tensile stress strain diagram of various plastics, right? So this is PMMA is acrylic, this is nylon, this is ABS, this is polypropylene, high density polyethylene, and low density polyethylene. This is what you will see in plastic. So there is a definite elastic region for some of them, okay, like these three, but it's very less. It's, let's say it's around 40 megapascals. It is nothing compared to metals, right? And for something, let's say like LDPE, there is almost nothing, right? So this is only for illustration purposes. Let's move on. And yeah, this will be there for you to see. Okay, let's move on to other things. Okay, So with this we come to these other material properties. So the first one is ductility. What do you think is ductility? Ductility is the amount of plastic deformation. That means the amount of change in dimension that the material can undergo before completely disintegrate, before completely breaking. Okay, so we are considering the whole range of the stress strain curve. Okay, it is not just the initial point where the material is elastic, but it's the whole range till you can completely break the material. So if you want a material which is ductile, okay, in nature, you would have to find something which has a ultimate yield stress, a fair, or not ultimate, the break point is quite higher. Okay, the strain, the amount of strain the material can show before coming to the break point is very high. Okay, so something like that. Here are some examples of elongation of in 50 mm percentage elongation and the reduction in area. So this kind of gives you an idea which ones are more ductile. So the steeper lines are, so copper and its alloys are a little more ductile than, let's say, aluminum, and carbon steel is somewhere here. Right? Oh, I'm sorry. So this is stainless steel, right? So the and this is copper and this is aluminum alloy. I think I'm reading it wrong. So I think these ones are a little more ductile in that sense. Okay. Anyway, so next we come to hardness. Again, there is a similar video, but we will run the whole thing to we will run the live stream for a bit too long if we watch it. So it's here, and
the Rockwell Hardness Test, Scale C. In this video, we will show how the Rockwell Hardness Test works using a gear wheel.
So rather than,
the basic idea of this test method is to measure the permanent depth of indentation of a hard indenter under a test force. In the process variant Scale C, a rounded cone made of diamond is used as an indenter.
I think it's not too long.
In step 1, the diamond cone is pressed onto the test piece surface with a minor force of 10 kilopons. The depth of indentation under this preliminary load is the reference point.
Right. By the way, before we go into this, we first of all have to know what exactly hardness is, right? What do you think hardness is? You can put it in the comments, or I will explain it to you and you listen, right? So hardness is basically the ability of a material to withstand indentation, right? Scratches. Okay, layman terms will put it as scratches. So have you done this before? Have you taken this? This is your cell phone, right? And this is my cell phone, not your cell phone. And this is a cutter, right? Should I do this? Some of you have who've seen Jerry Rig Everything videos would know that nothing happens if you scratch. Why? This is glass, this is steel. Glass is harder than steel. Okay. And yeah, Aditya, nothing really happens if you scratch it, right? If I really put my force into it also, I think, okay, just a second. Right. If I just right, nothing happens, right? Because glass is harder than steel. Okay, so hardness is basically a relative scale. So what material would a harder material would scratch a softer material? Okay, so diamond is the hardest material that way. Right? Glass is glass. Glass breaks, says Sanay. Glass definitely breaks, but we are talking about hardness, right? So hardness here is the ability to withstand scratches. Okay, and it's very difficult to there's no absolute mathematical way of measuring it. you can the only way of measuring it is, or right now the way in which it is measured is through a standardized test, and there are different types of standardized tests. So there is Brinell's standardized test, which is shown here, Vickers standardized test, Noops, and Rockwell is probably the most common one, and for different types of application different ones are used. So Rockwell is the most common one, and Rockwell hardness test is what the video shows you. There is a special type of a cone which is pressed onto the material, and uh, let's see the comments, because some of them are, I think, a little funny. Right. Vaibhav, sir, why do they say that scratch resistant glass breaks easily and durable glass gets scratched easily? I don't know if they say that, but I'm not sure. Okay, yeah. Nehul, flexibility, resist breaks, and flexibility and hardness don't go together. Okay. Well, that is kind of true, but I don't know if there's like a scientific, that's like a scientifically correct statement. Can there be something which is flexible and extremely hard? Probably not, right? Probably not. So I think Mehul is correct in that sense, right? Okay, so let's move on forward in the presentation. So similarly, Rockwell, you'll have Brinell hardness test.
The Brinell hardness
You
test.
see this video later, okay? Let's move on. And I want to introduce you to something called fatigue. So fatigue, Demon Gaming says scratches at level 6 and a deeper groove at level 7 is correct. I think you should put that link of the video somewhere. Anyway, okay. Right, so we are talking about fatigue. Fatigue is what is fatigue? When we say we are fatigued, that means we have done something for so long we are tired, right? Something like that. It's almost the same kind of analogy in material science also, right? Okay. So it is so if you take a piece of material and you put a cyclic load in it, what I mean by cyclic load is you put the load and you remove the load. You keep on this cycle going, okay? There will come a point where for materials like aluminium, after a certain number of cycles, it will break. You can test it very easily. You take two wires, one which you are definitely sure is aluminium, one which you are definitely sure is steel, and you keep on bending it one way or the other. Okay, like this, you keep on bending it, the aluminium one will break, okay, and most likely the steel one won't break, but it'll depend on the kind of force that you're applying or the material, the alloy, and so on, right? The aluminium will break. One thing is definitely sure, the aluminium will break much faster, right? That's because aluminium has a low fatigue strength, okay? What about carbon fiber? Isn't that hard and flexible, or am I wrong? Madhav asks. Carbon fiber, carbon fiber is a composite material, and the composite, if you say it is not just made out of the carbon fiber itself, it is also made out of resin. Okay, so if you take the composite itself, then if you scratch it, it will naturally get scratched. Okay, it is. So it will have a certain hardness which won't be considered too hard, right? It is not harder than diamond, definitely. But is it flexible? I don't think carbon fiber is flexible, is elastic. So we should use these terms very carefully. Okay, flexibility is even a very, so if you've seen glass fiber, Fiber reinforced plastics are made with glass fibers. No, glass fibers are long, thin strands of glass. If you take a thin enough strand, it is flexible. You can move it like this. If you just take fiber optic cables, okay, so these are also made out of plastic, transparent plastic. If they have a certain dimension, they will break. But these fiber optic cables are flexible in nature, right? So flexibility is a difficult term to. We shouldn't use it carefully. We should use it carefully, right? The correct terminology here that we should use is elasticity. Okay, so elasticity is a material, how much it can withstand force without having any plastic deformation, right? So if a material is elastic and can a material be elastic and hard? Yes, it can, right? Steel is a material which is elastic and harder than a lot of other materials which is softer than it. So again, hardness is a relative scale. Okay, so think about that. So this is fatigue, right? A material which has a higher yield strength can fail at much lower stresses if the stress is applied in a cyclic manner. This is what is written in the slide. Okay, and yeah, so this is the reason you don't use a material which has a low fatigue strength, where you are definitely sure that there is going to be cyclic loading. For example, if let's say a crankshaft of a car, okay, a crankshaft is there inside the engine block, right? So it rotates with the cranks, and the cranks exert a huge amount of force onto the crankshaft. Imagine if that crankshaft is made out of a material with definite fatigue limit. So after, let's say, something amount of cycles, it will fail at a very measly amount of stresses. Okay, so if that is the kind of things, then the car will definitely fail after so many times the engine has run. Okay, so many cycles of load. So that is why we use materials which show a property of endurance limit. Okay, so here this is for 1045 steel, a type of steel which shows an endurance limit. So beyond this, if you apply a cyclic load which is 300 megapascals, and this is the amplitude, the maximum amount of stress that is applied in the cycle, and if you go on you can go on indefinitely, right? So the material will not fail because it has an endurance limit just above 300 megapascal. Okay, if you take, however, a cyclic load of, let's say, 400 megapascal, it will definitely fail after so many cycles. So this is fatigue strength. Okay, and this property becomes very important in something called reliability engineering, where you want to find out what is the number of cycles a particular product can, or a number of load bearing cycles a particular product can withstand. So this property becomes very important, right? Among other properties. Okay, right. Okay, so as you can see, this is for plastics, and plastics have a definite endurance limit, and this shows you the ones of the various kind of plastic, right? Or not endurance limit, it's at fatigue point of breakage, right? Point of breakage because of fatigue. Right, okay. Let's go forward. Okay, toughness. What do you think is toughness? Let's see some of the questions. Okay, I'm sorry, I think even this is going to go on for some more time, but we'll go on till we reach one point. Carbon fiber is actually a fiber cloth before hardening. They just said you place a lot of layers and attach and harden them together, then it becomes strong. Somewhat correct, Tejas. You have to use a method of binding these fibers, because they don't actually stick together just like that. You have to have some form of material which binds these cloth or fiber cloth together. So this typically is some form of epoxy resin, but they have different things, and it's area of vast research. So I'm not sure what they use exactly in the real world right now, but you need to have some binding agent. Carbon fiber, Aditya says carbon fiber mostly depends on how it's made, right? Like it depends on what you mix in. It can be fragile or it can be flexible depending on the resin you mix. I think that's correct. Okay. Let's go on forward and let's see this property called toughness. Material property, another very important material, and there's a
The Charpy impact test.
very interesting test called the Charpy impact test, and let's see the video together. It's so much fun, and had you been here, I think we could have taken you to the mechanical lab and shown you these some of these tests, but yeah, well.
The standardized Charpy impact test has been designed to measure the toughness of materials under impact loading and multi-axial stress state. A pendulum impact testing machine is used to do so. The pendulum on the machine has a heavy weight at the end. This is lifted into the starting position in step 1.
Can we just say poor guy in the red sweater?
Then the tester checks whether the testing machine has been adjusted accurately. In order to do this, he turns the drag indicator downwards and releases the pendulum without a test specimen. The drag indicator stops at position 0. This proves that the pendulum has the correct starting position and that the friction is correctly compensated.
So basically,
the machine is ready for the tests. First test, strain-aged plain carbon steel S235. This is our test specimen. It has been machined to standardized size and shape with the characteristic V-shaped notch. The tester places the specimen on a support in the lower part of the machine and adjusts its position with a centering device. Next, he turns the drag indicator downwards again and checks that everything is prepared correctly. Perfect. The test can begin. The pendulum is released, it swings downwards and hits the specimen with its rounded hammer peen. The specimen absorbs part of the pendulum's energy, so the pendulum doesn't reach the full height on the other side.
Right, so you heard, because of the test piece absorbing some amount of energy, the pendulum doesn't reach the other side. And it's a very simple test. I mean, the construction of the whole thing is a very simple test, but it gives such an insightful,
The amount of energy that has been absorbed by the specimen can now be read off at the position of the drag indicator. It only amounts to 13 joules in this test. Here is the main principle of the measurement.
Right.
In its starting position, the pendulum only has potential energy.
See this after once you have these slides, and you can see the equations and all of that, right? So it is very easy to calculate the amount of energy that the specimen or the material has absorbed before it broke. Okay, so this is exactly what is toughness, is the amount of energy that the material can absorb before it breaks. Okay, so so what did I do? Okay, so that was toughness. I suggest, so there are a lot of details that I can't really add into this presentation in this format, but you should definitely go and see the texts around it. Okay, so these are the other ways in which the material can fail. Shreya says the guy looked like a stock image. Okay, so these are the other ways in which the material can fail. The first one that you see over here, I want the so the first one, right, where is the first one? Where is my cursor? Right, so the first one is a material with a definite yield point phenomenon. Okay, so it's a material which probably has a graph like this, right? So like this and like this. Okay, and this is the tensile stress. Okay, here what you see is sometimes what happens. So what do you think will happen when you have a perfectly straight rod and you press like this, right? If the rod is short and if the rod is long, you will have different behaviors that you will see. So let's say it's the same material, okay? So let's say it's something like it's steel, okay? So for a longer rod with a different kind of dimension, it will buckle, okay? It'll change its shape, it will go like this, okay? And this is called buckling. And here, however, what you will see is you will see a something like this happening. So it will barrel out, okay? It will get squished. I think there is also a YouTube channel where some guy just squishes things with a hydraulic press, right? So I don't know the channel name. I would have directed it to you. And now this is like different. If you do a tensile test and this image shows you different types of material and how these would fail, right? So here this is like a material with a distinct yield point phenomenon, what we saw in the video. This one is a very ductile material which kind of has a curve like this, pura smooth curve, something like this, till it fractures at this thing. And this one is, by the looks of it, okay, it is probably a slightly brittle material because of the way it is fractured. Yeah, hydraulic press channel is what Chaitanya says. I think that's the one. And this one is probably a material which has a very uniformly arranged crystal structure, where the fracture at one point, okay, if there is a breakage at one point, it just traverses to the other end through a boundary, okay, right? And if you see like a typical material here, if you see this portion, right, if you zoom in, this is what you will see. You will see how the breakage actually happens within the neck. It's just for information, but it is interesting to see. So I am pulling this material here, there is a neck which is formed, and the first thing which happens is that these nucleation sites form for the fracture, okay, and then these coalesce and they form a larger thing, and then the fracture actually happens, okay. So that is what was there. Right, so we come to an end of the just give me a second. Right, we come to the end of the material properties. That was a very basic overview, just the things that are important for us to consider. There are a lot of other material properties like creep, for example. What exactly is creep? I want you to find out for yourself, do a little bit of reading, and you can tell me. Like, what you can do is you can, in your own OneNotes, okay, you can write down these kind of, or okay, forget about it. I think we have an assignment for this. Let's watch an interesting video. Let's take a break, right? Okay, have you seen I don't know how many of you liquid carbon dioxide. Priyanshi says liquid carbon dioxide makes things float. Can we just say that this is like an amazing ad for a company to make something like this and show it. So less temperature, strong magnet. I know that, yeah, it's true. It uses superconductors, but what exactly is the property? Okay, I need, so you can't just say it's true, it is superconductors, it's true, it is magnets, and it's true. I'll show you how it's made. Okay, let's see how it's made. Okay,
We at Lexus always try to achieve the impossible. That is the attitude we apply to everything, with a constant desire to do what has never been done before.
It's like old stories, old fairy tales.
Nero says it's the same as eddy currents in electromagnets. Eddy currents in electromagnets produce heat in the electromagnets. Eddy currents produce heat and also magnetism, right? Of course. No, the phenomena has a distinct name. Okay, find it.
The flying corbett. And this is something close to that flying corbett.
Looks very unstable. Good.
It wants to go, doesn't it?
So you're right. Everybody said electromagnets. It's true. There is a magnet. Everybody said superconductor. That's true. Everybody said or some people said liquid nitrogen. That's true. But still, the question that does not answer the question: what is the material property which is making or which is being exploited to make this happen? Okay, that's the question.
Making a hoverboard isn't a straightforward process. We have had quite few ups and downs because it's normal when you are trying to do something truly innovative.
The system doesn't need electricity at all. We just use the superconducting material. We use a permanent magnet, and we use the liquid nitrogen to cool down the superconductor. You just have to keep it cold to have a long hovering effect.
The magnetic track has a certain magnetic field configuration, and this configuration is now also present in the superconductor. And when they are cooled down, then this field configuration is frozen in. When the superconductor stays in this position, it's an art of material science.
It's an art of material science. So imagine the amount of money they've put it into developing this, yeah. And for what? Advertising.
When I came in, I think it wasn't going in the direction everyone wanted it to go. But when I seen it, I was well excited about it. I was like, I want to have a go. Let's see what it is capable of. Yeah, within a week, we'd progressed loads. We'd gone from just going 5 meters in a straight line to going around the corner as fast as we could, and then we started setting up the jump and making it higher and making the gap bigger, and we progressed quick, really quick.
I think there were distinct parallels made with Back to the Future hoverboard, right? Yeah.
Some of the design elements, like the spindle grille
Sorry.
and also the bamboo deck of the board. We're almost exactly replicating what's inside the Lexus car. There's the science part of it, and then there's the design and the beautiful part of it where we get to make it look amazing.
Right, so they made this whole skateboarding arena with this embedded track.
The feeling of literally no friction and floating on air. It's hard to describe what that really feels like, man, but it's kind of like a science in yourself, in it. You know, you start to break it down. It starts to become less scary and less daunting, more fun. I started skating when I was about 7 or 8. It literally feels like I'm starting all over again from the beginning. Now I'm really was born again, and then look, here's a skateboard, learn it.
It's amazing. So that's how it was done. Let's move on.
Superconductivity is a fascinating
again,
phenomenon.
the video will be there
Strings.
for you
Maybe,
to watch. And how do they stop it? They let it crash onto a softer surface, I think. Aditya asks, does this have any uses in the future, or is it just Toyota make money flex science project? I think it has tremendous amount of real world application, right? In transportation itself, let's say in like these trains and all that, you could have these kind of technologies in the near future. I mean, there is right now, to as the best of my knowledge, there doesn't exist a superconductor which works like a superconductor in room temperature or in higher temperatures. So you always have to cool it down to achieve that property. And but I think, I mean, as soon as you do that, interestingly, that is the whole plot of a film called Avatar, which brings us to the assignment. And right, they just follow and let it stop whenever. Aditya's okay. Black Panther floating trains. Yeah, like those Wall-E in those flying seats. Yeah, everything in science fiction, everything floating in science fiction can be explained potentially with superconductors. Okay. It does not work without the track developed here, right? Okay, anyway, so here, this is our assignment for the second assignment for this module, and it is to find an interesting material which has an interesting property. Okay, you have to find as far as possible, you have to find the original scientific tests that discuss these properties and explain these properties to you, and you have to make a concept product. So what you saw in the Lexus video is they have an interesting scientific property. I will still leave it up to you to find it. Okay. Somebody did mention it's quantum locking. Yes. Right. Okay. Okay. Right. So similarly, yes, Vignesh, unobtainium is a superconductor material, and if you go back and look at Avatar, the film, I mean, you have to give it to James Cameron, because everything in that film makes sense. So the people of Earth want this unobtainium, which is apparently a superconductor. This unobtainium material is making those mountains float in the air because of the gravitational field is underneath it of the planet, and the mountains containing superconductor. It kind of, you can explain a lot of these things that happen in the film, right? I think even the cultural aspects of the Navi tribe you can explain because of the existence of this material. It's an amazing, if you go and look and decipher it, no, from this world building perspective, it's an amazing film. Anyway, so I am digressing again. So you need to make a conceptual product. What you saw on the Lexus hoverboard, they took a material property and they made a concept product. Okay, they made it in reality, but for you, I don't think you have to make it in reality. You have to make a concept of that product. You have to make a sketch or a render or whatever you are comfortable with to explain that two things. Explain that material and the property. Then you have to reference as far as possible the original scientific texts where random internet websites where or popular science news articles probably won't cut it. Go deeper and try to understand what makes this property unique, how material scientists have figured out about this property, how they've tested it, and so on. And then with that knowledge in hand, get that idea, get the knowledge with you, and then develop a product. Okay, develop a concept product. So I can show you some of the examples that people have done. So remember that this assignment is being done for the third time now. Your batch will do it for the third time now, and I've seen most of it. I've seen most of the things, most of the materials that people submit. Okay, like Venta Black, it's common. Okay, everybody knows Venta Black. Like for example, self-healing concrete. Everybody knows about self-healing, or rather, I know about self-healing concrete. Spider silk. Okay, everybody knows about spiders, or I know about spider silk. I know about carbon nanotubes or graphene, material called graphene, or anything related to graphene. If you don't do graphene, okay? Everybody does. Sci-Hub, if you face paywalls looking for research papers, Chaitanya, I don't endorse piracy. Okay? But you do what you have to do to get access to research. I think there's a VPN connection that you can establish to the institute, and you can access the library portal that way, and you can access the scientific papers. Besides that, I mean, you do what you have to do to get access, right? So I gave you one way. Can we see our seniors' assignments? Hardika asked. We can see. Okay, let's see. Okay, we'll try and see. Okay. What else have I seen? I've seen those blocks that are used in the space shuttle, which can absorb a lot of heat and dissipate it so quickly that you can kind of pick it up when it is red hot and so on. So anything viral, I've seen. Okay, so you need to find something which is not gone viral yet. Okay, so some material property which is not gone viral yet, which is interesting. Aerogel, of course, Anirudh, everybody knows aerogel. Okay, I know aerogel's father also. Like, there is a new version of aerogel that has come out, so that also I know. Okay, right. What else? Okay, forget about it. So as far as possible, try to find something which is a little non-viral, which is, that you are fairly confident that people won't know about it. If it's being written in popular science articles, probably, I mean, people will know about it. But then again, you can take a bet and you can drop me a mail if you think, I think we should do a running chat. We can do it in the collaboration space of the OneNote. So if you have doubts, just put it in there. Sir, can I take this material? Okay, I can answer it then. Okay. Right. Non-Newtonian fluid. Madhav, yes, I know about non-Newtonian fluid. It is just cornstarch and water. Okay. And it is special. It's a special property. But it's just cornstarch and water. It's okay, right? Anyway, okay. Right, so you need to, what you have to, what will I judge this on is, I'll see if you've done your research. I'll try to see if you, the way you've written it, it's interesting. I mean, I have learned something new about it. And then the second thing is, you need to really exercise your creative muscles and show me something very unique that I have not thought. It's difficult to think. Ace is not in the OneNote thing. Ace I will add you to that. Okay. If anyone else is not there, just put in the message. I will add it. And then finally, it's the details. If you are able to show the details in the product, then it will be an interesting one. Okay. So this one you submit it in OneNote, or what you can do is, no, you submit it in OneDrive only. You can put a link in the OneNote folder of the submissions, and if that way it's a record also. So you put it in OneDrive, anything, PDF, presentation, whatever. Try to make it less data intensive. And yeah, sir. So Gaurav, so let's answer a few questions. I think there were a few questions from back. Right. So do we submit just the concept or the research too? Well, let's just say you have to make like at least one page of, let's say, what is the material, what is the research property, why it is interesting, a write-up. The second page is, let's say, you designing the concept, what is this concept and how does it work. And the third page is a presentation of that concept, that is interesting images, 2 or 3 images of that, or 1 or 2, a presentation like of that product concept. Okay, design it well enough that you can add it later on with very little modification. You can add it to your Behance portfolio. Okay, it's or you can post it on Instagram or something like that. Okay, design it at least to that quality. Okay, yeah, right. So are there any questions? It's a long lecture. Let's see how many people are there. Right, not too many people. I think people left in the middle. So yeah, okay. So I think we'll conclude the lecture over here, and we'll start off back tomorrow. Is a 3D render? No, it's not necessary. I never said 3D render. I only say, I'm saying it rendering. By rendering, I mean it needs to be a good drawing, right? A good representation, a good visual representation. You can use 3D or you can use your 2D skills to present it. Okay, any which way. Okay, so yeah. So with that, we will finish this course here. We will finish this class here, and it's already evening also, and the stream has been going for so long. Thank you guys for whoever has stayed till the end. Thank you for that, and whoever joined in also, thank you for that. And the video will be available for you on YouTube. You can come back and relook at it. And yeah, if you find some information around these things, leave a comment in the video so that somebody else, when they come in and see the video, they can find the comment and it will be interesting, right? Okay, so yeah, thank you so much. I'll end the live stream here, and I will see you. I'll see you tomorrow at the same time, same way. Okay. Right, okay. I'll see you guys tomorrow. Join at 3 o'clock, same time. I'll try to keep it short tomorrow, but yeah, let's see. Okay, we have a lot to cover. Thank you so much, guys, for joining in. Thank you. Bye.